You see that little symbol on your screen pretty much every day, right? It's probably one of the most recognized icons on the planet. But behind those simple little curves, there's this incredible world of complex engineering, a really surprising history, and some seriously elegant physics. So let's dive in and pull back the curtain on how Wi-Fi actually works. And when I say it's everywhere, I am not kidding. Just look at this. We are talking about billions, with a B, of Wi-Fi chips shipping in a single year. These are in our phones, our cars, our coffee makers, our hospitals, you name it. The scale is just staggering. So what is this invisible language that all our devices are speaking?
All right, so to really get started, you've got to get one thing straight right off the bat. The name Wi-Fi itself, well, it's not what most people think it is. And figuring that out is our first step into this hidden world.
Okay, so here's the big secret. Wi-Fi doesn't actually stand for wireless fidelity. Turns out that was just a catchy marketing tagline they came up with later. In reality, Wi-Fi is a brand name. Think of it like a seal of approval. It's a certification that tells you, hey, this device meets a very specific technical standard called 802.11, and it's guaranteed to play nicely with all the other certified gear out there.
That idea of certification brings us to the rule makers. You know, for billions of devices to talk to each other without total chaos, you need a whole system of organizations all working together. It's this quiet, global ecosystem that keeps our digital world running. Let's break down who's who.
First up, you've got the Wi-Fi Alliance. These are the testers and the marketers of the Wi-Fi world. They're the ones who make sure that a laptop from one company can talk perfectly to a router from a totally different company. When you see that Wi-Fi certified logo on a box, that's them. They're the guardians of compatibility. But if you go one level deeper, you find the real architects, the Institute of Electrical and Electronics Engineers, or just the IEEE. This is where the magic really happens. The IEEE is made up of engineers who literally write the blueprints for Wi-Fi. They're the ones who come up with these super technical standards like 802.11ax. And what's really cool is how these two groups work together. I mean, let's be honest, 802.11ax doesn't exactly roll off the tongue, right? So the Wi-Fi line stepped in and did us all a huge favor. They created a much simpler naming system. So 802.11n became Wi-Fi 4, .ac became Wi-Fi 5, and .ax became Wi-Fi 6. So much easier. And then, sitting at the very top of all of this, you have the regulators. Think of them as the air traffic controllers for the airwaves. Globally, you have the ITUR, which is part of the UN, and they coordinate who gets to use which radio frequencies around the world. And then here in the US, you've got the FCC, who manages our slice of the pie, making sure your router doesn't interfere with, say, your neighbor's baby monitor.
Okay, so we've got the rules and we've got the rule makers. But how does your data actually, fly through your house? Well, it all comes down to the beautiful fundamental physics of radio waves.
At its very core, Wi-Fi is just radio. It uses these invisible electromagnetic waves to carry information from one point to another. And the key to the whole thing is that we can change a simple, plain wave in very specific ways to encode our data onto it. There are three main properties we can play with. First, you've got amplitude. The easiest way to think about this is that it's just the power, or the strength of the wave. It's basically the volume knob. A higher amplitude means a louder, stronger signal, and a lower amplitude is a quieter one. Simple as that. Next up is frequency. This is just how fast the wave is oscillating up and down. We measure it in hertz. Now, get this. When your router says it's using the 2.4 gigahertz band, that means it's creating 2.4 billion of these little waves every single second. The speed is just mind-blowing. And finally, we have phase. Now, this one's a little more abstract, but stick with me. It's all about timing. If you have two identical waves, phase describes the starting point of one wave relative to the other. As you can see here, we can shift that starting point, and we measure that tiny little shift in degrees. So we have our three tools: amplitude, frequency, and phase. Now comes the really cool part. Let's see how Wi-Fi uses those three things to create a language, to translate the simple ones and zeros of your computer into a signal that can literally travel through thin air. So the whole process starts with a really simple continuous radio wave. We call it a carrier signal. It's basically a blank slate. Then, to encode data onto it, we start messing with its properties. We alter or modulate it. Each one of those little alterations stands for a piece of binary data. This whole technique of manipulating the wave is called keying.
The most basic method is amplitude shift keying, or ASK. It's super straightforward. We just change the wave's height. A high amplitude wave could mean a 1, and a low amplitude wave could mean a 0. It's pretty much like sending Morse code by shouting for a 1 and whispering for a 0. Then you've got frequency shift keying, or FSK. So instead of changing the volume, now we're changing the pitch. A faster, higher frequency could be a 1, and a slower, lower frequency could be a 0. It's just another way to signal a difference. And finally, there's phase shift keying, PSK. This method is way more sophisticated. Instead of just looking at the state of the wave, the receiver is looking for a change in its pattern. A sudden shift in the wave's phase is what signals a bit of data. This is really clever because it's more resistant to noise, and it's a fundamental part of how modern, high-speed Wi-Fi works. So now we know the what and the how. We get the rules, we get the physics. But the story of who and when, well, honestly, it's one of the most fascinating and just plain unexpected stories in the history of technology. And believe it or not, it all starts right here. This is a U.S. patent from 1942, smack in the middle of World War II. It's for a secret communication system designed to guide torpedoes remotely. The core idea was something called frequency hopping, rapidly switching between radio frequencies so the enemy couldn't jam the signal. This concept is a direct ancestor of the wireless tech we all use today. So who was the brilliant mind behind this critical military tech? A team of government scientists in a secret lab? Nope. The lead inventor listed right there on that patent is Hedy Lamarr. Yes, that Hedy Lamarr, one of the most famous, glamorous Hollywood movie stars of the 1930s and 40s. It's absolutely true. A movie star helped invent a core principle of modern wireless communication. Okay, let's fast forward a bit. The next giant leap forward came in 1970 from a team at the University of Hawaii. They built something called AlohaNet, which was the world's first wireless computer data network. They needed a way to connect computers across the different Hawaiian islands, and in doing so, they pioneered a system for devices to avoid talking over each other on a shared network, a problem our gadgets still have to solve every single day. And finally, all these different pieces of the puzzle, the secret WWI patent, the network in Hawaii, decades of engineering work, it all came together in one pivotal year, 1997. That's the year the IEEE officially ratified the very first 802.11 standard. This was the moment. The technology we now just call Wi-Fi was officially born, and it laid the foundation for the connected world we all live in. So we've gone from that simple symbol on a screen all the way through a global network of rulemakers, the elegant physics of radio waves, and a secret history that stars a Hollywood icon. It's an incredible story. So the next time you connect, maybe you'll remember everything that's hiding behind those little curved lines. It really makes you wonder, doesn't it? What will the next generation of wireless make possible?